In the last class, we started discussing about linear programming problem. So, linear program is a mathematical program where the objective function is linear and the constraints are linear in the variable. So, we started discussing about some of the properties of the constraint set, and we looked at what are called the extreme points of the constraint set. So, in this figure, the shaded region is the constraint set, and we defined extreme point as for a convex set X, a point X is an extreme point that is also called a corner point or a vertex of X if X cannot be represented as a strict convex combination of two distinct points in X. So, for example, in this figure, the points A, B, C and D are the extreme points, while the point E is not an extreme point. Now, here is another example of a constraint set. Remember that the constraint set in a linear programming problem is a convex set, and the objective function being a linear function is also a convex set. So, the linear program is a convex programming problem. Now, the constraint set could be bounded or unbounded. So, here is an example where the constraint set is unbounded and this has only one extreme points. Sometimes if the constraint set is just the half space associated with a hyperplane, then that constraint set does not have any extreme point or a vertex. So, a typical linear program may have 0 vertices or 1 vertices or more than 1 vertices. So, we saw that if we have the constraint set which is the half space shown by the shaded region, then this constraint set does not have a vertex. So, the only extreme point in this case is the point A. Now, let us see more about this constraint sets. So, consider the constraint set as a pair of points x1, x2 such that x1 plus x2 less than or equal to 2, x1 less than or equal to 1 and x1 and x2 both non-negative. Now, we have 4 constraints in this set X. Now, if we take a point, extreme point or a vertex, you will see that in this 2-dimensional space, only 2 constraints are active at the extreme points. For example, if we take point C, then the constraint x1 plus x2 is equal to 2 is active, and the constraint x1 equal to 1 is active, and C is the intersection of these 2 constraints. Similarly, if we take the point A, then the last 2 constraints are active and the other 2 constraints are inactive. On the other hand, if we take a point like the point E, which is in the interior of the set, we will see that none of the constraints is active at this point. On the other hand, if we take a point on the line segment joining say the points B and C, then only the constraint x1 equal to 1 is active, while the rest of the 3 constraints are inactive. So, we can conclude that in this case, when we have 4 constraints in 2-dimensional space, at the extreme points, we have 2 constraints which are active. Of course, there could be situations where more than 2 constraints are active at an extreme point in this 2-dimensional case, but then one of those some of those constraints will be redundant. For example, if you consider the similar situation. So, suppose that this is our constraint set. And if we are considering this point, then this constraint and these constraints are active at this point. Now, one could have an extra constraint which is like this. Now, you will see that this constraint is redundant constraint. So, when we have three constraints which are active at a extreme point in two dimensional space, one of the constraints can be treated as redundant constraint. So, in effect there will be only two constraints which are active. So, one can think of it like this, that if we take the hyperplanes corresponding to those active constraints and take the normals to those hyperplanes, the two normal directions are linearly independent in this case. Okay. So, in the example which is shown here, we have only two constraints active at extreme all the extreme points, and then fewer than two constraints are active at other points. So, on the line segment joining the vertices, we have only one constraint which is active, and in the interior of the constraint set we have no constraints which are active. Now, suppose if we consider the constraint set of the form the set of all points x such that x less than or equal to b and x greater than or equal to 0, where A is a m by n matrix of real numbers and rank of A is m, then there are m plus n hyperplanes associated with the m plus n half spaces. So, remember that there are m constraints associated with x less than or equal to b and n constraints associated with x greater than or equal to 0. So, in all we have m plus n constraints associated with the constraint set x. So, m plus n constraints means that we have m plus n hyperplanes associated with those m plus n half spaces. Now, these m plus n half spaces together define the set x, and an extreme point lies on n linearly independent defining hyperplanes of x. So, out of this m plus n half spaces, we will be interested at an extreme point on n linearly independent hyperplanes. Remember that the x is in n dimensional space. So, at an extreme point we have n linearly independent defining hyperplanes of x, and if x is non-empty, then the set of extreme points is not empty, and this set x has finite number of extreme points. So, this is a very important observation. So, we will prove this fact related to a general constraint set sometime later, but remember that if x is non-empty, then the set of extreme points of x is also not empty, and further the set has finite number of extreme points. Now, let us define an edge of the set x. Now, as we saw in the previous case that on the line segment joining the two vertices, the number of constraints which were active were n minus 1. So, edge is formed by the intersection of n minus 1 linearly independent hyperplanes, and two extreme points of x are said to be adjacent if the line segment joining them is an edge of x. So, we will take some example to illustrate this. So, the line segment joining the two vertices b and c is called the edge, or in other words, the edge connects the two adjacent extreme points. So, the points B and C are adjacent extreme points or adjacent vertices. Similarly, points C and D are adjacent vertices, and the line segment CD connecting the two vertices C and D is also an edge. Now, you will see that on the edge there is only one constraint active in this two-dimensional case. So, the edge is typically defined by n-1 linearly independent hyperplanes that define the constraint set X in n-dimensional space. So, adjacent extreme points have n-1 common binding linearly independent hyperplanes. So, those are the hyperplanes which are active associated with the edge. Now, let us see some remarks about the equality constraint set, like the set of all x such that Ax equal to be x greater than or equal to 0, where again A is a m by n matrix of real numbers and the rank of the matrix A is m. Now, let us take an extreme point of x and let us call it as x bar. Now, since x bar belongs to x, it has to satisfy all the equality constraints, because at every feasible point all the equality constraints are active. So, there are m equality constraints which are active at x bar, and since it is an extreme point, we know that there are n linearly independent hyperplanes defining the extreme point x bar. So, out of n, m constraints have come from the equality constraints. So, the remaining n minus m active constraints come from this part x greater than or equal to 0. So, that is n minus m additional hyperplanes coming from x greater than or equal to 0 are active at x bar. So, out of n constraints which are represented by x greater than or equal to 0, n minus m are active. That means that corresponding to those variables, the value of x is 0. Now, let us look at the geometric solution of a LP. So, to understand how to solve a given linear programming problem, the geometric solution gives us a good idea, and that can be used to devise efficient algorithms to solve an linear program. Now, this geometric solution typically is useful when a linear program is in 2 dimensions. So, we will consider some such cases and show how the geometric solution of a given linear program can be obtained. So, let us consider a program which is of the type minimize C transpose x subject to x greater than or equal to b, x greater than or equal to 0, where A is the m by n matrix, C is a n dimensional vector and B is a m dimensional vector. Now, let us assume that the constraints are such that we have a non-empty feasible set. So, for example, here is a 2-dimensional case where we have 2 variables x1 and x2, and the constraint set is the set of half spaces defined by these constraints. So, there are 4 constraints of this type and then 2 non-negativity constraints corresponding to x1 and x2. So, these together form a feasible set. So, the interior of this polygon is the feasible set. So, to avoid any notational, to avoid any clutter in the figure, I have not shown it as a shaded region, but the entire boundary as well as the interior of this polygon denotes the feasible set. And assume that the vector C is as shown here, and our aim is to minimize C transpose X subject to the constraint that X belongs to the feasible set X. So, let us see how to do this. Now, we know that C is pointing in this direction. So, the objective function decreases when we move along the direction minus C, because in this half space, if we consider the hyperplane which is perpendicular to C, so that will be denoted by C transpose X equal to 0. So, in the direction where C is pointing, C transpose X is greater than 0, and in the direction of minus C, C transpose X is less than 0. So, obviously, the objective function decreases when we move along the direction minus C. So, what we need to do is that take the hyperplane which is parallel to this hyperplane C transpose X equal to 0 and keep moving that hyperplane along the direction where the objective function decreases, and we maintain the contact with the set, the feasible set X, and there will be some point where the function value will have minimum. Now, there may be situations where the minimum may not exist. So, such problems are called unbounded problems, and we will not worry about those cases at this point of time. Let us assume that the minimum does exist, and let us see how to find out a one. So, here is a hyperplane which is parallel to the hyperplane C transpose X equal to 0. That means that the normal to the hyperplane is still C, but the intercept on the axis are different. So, here is the equation of a hyperplane C transpose X equal to alpha and another hyperplane C transpose X equal to beta, and as we have indicated earlier that the objective function value decreases when we move along the minus C direction. So, obviously, beta will be less than alpha. So, if we keep moving this hyperplane further, we may come across a point where we get the minimum of the objective function with respect to this constraint set. So, if we move this hyperplane further, then we will hit the solution point of the given problem. Now, remember that if we move this hyperplane further, we will not satisfy the constraint set X. So, this point appears to be the solution point of the given problem, minimize C transpose X subject to this constraint set. Now, there may be situations where the solution point may not be unique. So, let us see an example. So, let us consider a different C vector, different from the one that we saw earlier, and the constraint set is still the same, and this is the hyperplane C transpose X equal to 0. So, our method should start constructing hyperplanes which are parallel to this hyperplane, and that has a non-empty intersection with the feasible set. So, if you start constructing those hyperplanes, so obviously, C transpose X equal to alpha is this hyperplane and C transpose X equal to beta is this hyperplane, and beta will be less than alpha. And if we go on moving this hyperplane further, we will see that we get the solution, but this time the solution is not unique. So, what I mean by the non-uniqueness of the solution is that there exists different x which will give us the same objective function value. So, the objective function value, optimal objective function value is always unique, but the set of x which gives these optimal solutions may not always be a singleton set. So, here is an example where we have infinitely many optimal x's which give us the same optimal objective function value, that is C transpose x star. Now, let us consider an example. So, we have problem minimize minus 2 x 1 minus x 2 subject to the constraint x 1 plus x 2 less than or equal to 5, x 1 plus 2 x 2 less than or equal to 6, and x 1 and x 2 are non-negative. So, let us draw the constraint set. So, x 1 plus x 2 equal to 5 is this line, and x 1 plus x 2 less than or equal to 5 is the half space denoted by this arrow. Similarly, x 1 plus 2 x 2 equal to 6 is this line, and the set x 1 plus x 2 less than or equal to 6 is denoted by this arrow. Now, the intersection of these two half spaces along with the fact that x 1 and x 2 are non-negative. So, this indicates that x 1 is greater than or equal to 0, and this indicates the half space where x 2 is greater than or equal to 0. So, the intersection of these four half spaces gives us the constraint sets, which is shown by the shaded region. Now, let us take the C vector, which is minus 2 and minus 1, which is shown here. So, if we move along the direction minus C, the function value decreases. So, for that purpose, let us first take the hyperplane which passes through origin and which has normal as vector C. So, this is this hyperplane which is shown by the shaded line. So, the idea is to move this hyperplane in the direction of minus C, such that the hyperplane, each of those hyperplanes has a non-empty intersection with the feasible set, and we keep moving it till we get till we cannot move further, and at that point we get the minimum. So, the value of the objective function at any point on this, at any feasible point on this hyperplane will be greater than the value of the objective function at any feasible point on this hyperplane. So, if we keep on moving like this, we will reach a situation where we cannot move that hyperplane further without violating the constraint. And at this point we stop, and you will see that this is an optimal solution. In fact, this is the only optimal point in this case. So, you will have noticed that the optimal solution always lies at the boundary point if the optimal solution exists. There may be linear programs where the optimal solution may not exist. Those linear programs are unbounded linear programs, and whenever we say that the optimal solution exists, we mean that the optimal solution is finite. Let us consider a general case, minimize C transpose x subject to x belongs to x, where x is a convex set. Now, in this case, the set is unbounded and convex, and assume that the C vector points in this direction. Now, C transpose x equal to 0 is this hyperplane, and we want to move in the direction of minus C. So, if we consider any feasible point and start moving in the direction of minus C, suppose we start from this hyperplane and then start decreasing the value of the objective function, finally, we will reach a point where we cannot decrease the objective function value further without violating the constraint. So, this turns out to be the optimal solution of the given problem. So, the example illustrates that even if the constraint set is unbounded, in this case, there does exist the optimal solution. On the other hand, if we take the vector C to be pointing in this direction, and if you want to minimize this objective function C transpose x subject to x belongs to x, then and if you start from this, then in this direction the objective function decreases and the constraint set is unbounded. So, the minimum will not exist. So, such a problem is called unbounded problem. So, I repeat that whenever we say that the optimal solution exists for a linear program, we mean that the optimal solution or optimal objective function value is finite. Note also that as we have seen that the number of optimal points, the number of optimal x's could be either 0 as in this case when the problem is unbounded, or 1 where we get the optimal solution at the vertex, or the number of optimal x's could be infinitely many. An entire edge of the set X can be part of the set of optimal solutions, but the optimal objective function value, if it exists, is always unique. So, let us consider a linear programming problem where we minimize C transpose x subject to ai x. It will be either less than or equal to bi or equal to bi or greater than or equal to bi. So, we have either types of constraints in our constraint set, the less than or equal to type, the equality type or greater than or equal to type. But whatever is the case, the constraints are always linear in x, and assume that there exists non-negativity conditions on x, or there are non-negativity constraints on x. So, let us assume that or let us denote the constraint set by capital X. So, capital X is the set of all x's such that ai transpose x less than or equal to or greater than or equal to bi depending upon the case. There are m such constraints and we have non-negativity constraints. Now, we have already seen that each constraint denotes a closed half space, and therefore, this constraint set X is an intersection of closed half spaces. Now, each half space is a convex set. So, we have intersection of closed convex sets, and therefore, X is a closed convex set. We have seen this fact earlier when we discussed about convex set, that intersection of an arbitrary collection of convex sets is a convex set. So, here each constraint set is also closed, and therefore, the intersection of closed convex sets is a closed convex set. Now, the objective function is also a convex function, and therefore, we have the convex programming problem. So, every linear program is a convex programming problem, and as we have already shown that the set of solutions or set of optimal solutions of a convex programming problem is a convex set. Now, we have seen so far by examples that a typical linear program may have no solution. Now, there are different cases related to this. One possibility is that the constraint set is unbounded and the problem becomes unbounded because of the nature of C. So, remember that there could be situations where the constraint set is unbounded, but there exists a unique solution which is bounded. So, if the constraint set is bounded and the vector C is such that the optimal objective function value may not exist for a linear program, then we say that the problem is unbounded. In such a case, no solution exists. The other possibility is that the set X itself is empty. So, then obviously there is no solution to the linear program. We also saw some cases where there exists a unique solution, and we also noted that the unique solution does exist at the vertex or an extreme point of the set X, and there is a possibility that a linear program may have infinitely many solutions. Now, we also note that if X star is an optimal solution to LP, then X star must be a boundary point of X, which means that X star cannot be a solution, an optimal solution to LP, and is in the interior of the set. Now, let us quickly see why this is not possible. So, let us assume that the constraint set is this set, and let us assume that the solution lies in the interior of the set. Now, if X star is in the interior of the set and X star is an optimal solution to the linear program, since the point lies in the interior, we know that there exists a circle of radius epsilon around X star, such that that circle, the ball of radius epsilon around X star is contained in X. So, there exists some epsilon greater than 0, such that a ball of radius epsilon around X star, it is contained in the set X. So, let us assume that the vector C is pointing in this direction. So, that means that if we move along the minus C direction, we decrease the objective function. So, let us take a point X to be X star minus epsilon by 2 along the direction C by norm C. So, in this direction, in the negative C direction, we take a point. So, suppose this is a negative C direction. We take a point which, so we take a point X. Now, remember that X star is, we have assumed that X star is unoptimal to a linear program. So, therefore, C transpose X star is less than or equal to C transpose X for all X belongs to X, because X star is optimal. And suppose X star lies in the interior. So, there exists a ball of radius epsilon around X star which contains in X. So, let us take a point X in that ball. Now, let us see what happens to C transpose X. So, C transpose X is equal to C transpose X star minus epsilon by 2 norm C, because this will be C transpose C, which is norm C square divided by norm C, will become norm C. Now, epsilon is positive. So, remember that epsilon is positive. So, norm C is positive. So, therefore, C transpose X will be strictly less than C transpose X star. So, that means that there exists a point X in the set X such that C transpose x is less than C transpose x star, and this contradicts the assumption that x star is a minimum, because if x star had been minimum, C transpose x star would have been less than or equal to C transpose x, and we get the contradiction, and therefore, x star cannot lie in the interior of the set X. So, it has to lie on the boundary point of the set X. Now, if x star is a solution, let us take Z to be C transpose x star, then the set X such that C transpose x equal to Z is a supporting hyperplane to the set X. So, if we take along the minus C direction, the objective function decreases, and finally, we get a plane, in this case a line, which is a supporting hyperplane to the set X, and this point turns out to be the minimum point. So, you will see that at the optimal point or the optimal x, the supporting hyperplane C transpose x equal to C transpose x star is the supporting hyperplane for the set X, and it supports from below. Now, here is the important result. It says that if X is compact, so not only that X is closed, but X is also bounded. So, if X is closed bounded convex set or a compact convex set, and if there exists an optimal solution to LP, then at least one extreme point of X is an optimal solution to the linear programming problem. So, we will prove this result later on, but what is important about this result is that, so if you see the previous statement, we said that if x star is an optimal solution to LP, then x star must be a boundary point. Now, there may be infinitely many boundary points on the set X, but then if X is compact, then we need to search only for the extreme point or the vertices of the set X to get an optimal solution to LP. So, finding the solution of an LP becomes an easy task, because what one has to do is just to search over the set of extreme points. So, although this procedure is inefficient, but it gives us a way to solve the given LP in a simple way, just to search over the set of extreme points. Now, the natural questions that arise are whether there exist finitely many extreme points for a constraint set, and how do we characterize these extreme points algebraically. So, we will start looking at those things. Now, before we go into the details, let us look at the linear program in standard form. Now, different textbooks use different notations for standard forms, but in this course, we will follow this notation where we define the linear program in standard form as minimize C transpose x subject to x equal to b, x greater than or equal to 0. So, the objective function is linear. More importantly, the constraints are of the type Ax equal to b. So, that means that we have all equality constraints. There are no less than or equal to type constraints in this Ax equal to b, and all the variables are non-negative. So, this is the only constraint which is inequality constraint, that the variables are non-negative. So, when we have a program in this form, we call it a linear program in standard form. So, there are m equality constraints. So, which means that A is a m by n matrix of real numbers and rank of A is equal to m. Now, we also assume that the rank of A and the rank of A appended with B is same. In other words, B lies in the column space of A. So, that means the system of equations that we have is consistent and the feasible set is non-empty. So, this is what we assume for linear programs. Now, the importantly, any linear program can be written in this form. So, let us see how this can be done. So, this is a very important observation. Now, there are different possibilities that instead of minimization, we may have a maximization problem, or there could be some constraints where there is a less than or equal to kind of inequality, or there could be some constraints where there is a greater than or equal to kind of inequality. Further, the non-negativity constraints may not always be there, but despite all that, we can always convert a linear program, any linear program, to the standard form, and let us see how to do that. So, a maximization problem can be always written as a minimization problem, and we have seen that earlier also. So, maximize C transpose X can be written as minus minimization of minus C transpose X. So, therefore, even if any linear program has a maximization problem, we can always convert it to a minimization problem. Now, if the constraint is of the type A transpose X less than or equal to B and X greater than or equal to 0, so we have an inequality constraint, and that can be converted to the equality constraint problem by introducing what are called slack variables. So, this constraint can be written as A transpose X plus Y equal to B. Now, this Y is a non-negative number. So, therefore, the given constraint which is of the type less than or equal to is converted to an equality constraint by introducing a slack variable Y. The other constraint remains the same. Similarly, if we have a constraint of the type A transpose X greater than or equal to B and X is non-negative, that can be converted to A transpose X minus Z equal to B. So, Z is called the surplus variable and Z is non-negative. So, any inequality of the type A transpose X greater than or equal to B can be written as a linear equality constraint by introduction of surplus variable, and of course, that surplus variable is non-negative. So, thus any constraint of the type A transpose less than or equal to B or A transpose greater than or equal to B can be written as an equality constraint by having some slack or surplus variables depending upon the case. Now, the only question that remains is that what about the variables which are unrestricted in sign? So, the free variables, for example, xi belongs to R, they can be defined using some extra variables. So, for example, xi can be written as a difference of two non-negative variables. So, xi plus and difference of xi plus and xi minus, where xi plus is non-negative and xi minus is also non-negative. So, any free variable can be written as difference of two non-negative variables, and this is what is shown here. So, let us take an example to illustrate this before moving further. So, let us consider the problem to minimize x1 minus 2 x2 minus 3 x3 subject to x1 plus 2 x2 plus x3 less than or equal to 14, x1 plus 2 x2 plus 4 x3 greater than or equal to 12, x1 minus x2 plus x3 equal to 2, and x1 and x2 are unrestricted. So, which means that x1 and x2 can be any real numbers, and x3 is less than or equal to minus 3. Now, given this program, suppose we want to convert it to the linear program in standard form. Now, we have already seen that the constraints of the type less than or equal to can be converted to the equality type constraint by introduction of slack variable, and the constraints of the type greater than or equal to can be converted to equality constraints by introduction of surplus variables. So, we will need one extra variable for this constraint, and those two variables are non-negative. So, that is not a problem. The third constraint is equality type. So, we do not have to worry about that. But now, the question is that we have some variables which are unrestricted, and then there is a constraint on x3 to be less than or equal to minus 3. So, how do we convert all these variables x1, x2 and x3 to the variables which are non-negative? So, let us see that. So, let us first write the constraints as equality constraints by introduction of slack or surplus variables depending upon the case. So, if we take the first constraint, then we have to add a slack variable to make it a equality constraint. So, x1 plus 2 x2 plus x3 plus x4 is equal to 14, where x4 is non-negative. So, x4 is a slack variable. Now, similarly, for the second constraint, we can remove the surplus variable to make it a equality constraint. So, x1 plus 2 x2 plus 4 x3 minus x5 equal to 12, x5 non-negative. Now, third constraint will remain as it is. So, we do not have to worry about that, and now we have to worry about the variables. So, since x1 and x2 are unrestricted, what we can do is that we can define the variables x1 plus and x1 minus and x2 plus and x2 minus, such that x1 can be written as the difference of x1 plus and x1 minus, where x1 plus and x1 minus are both non-negative. Similarly, for the variable x2, because it is also unrestricted in sign. So, x2 is equal to x2 plus minus x2 minus, where x2 and x2 plus and x2 minus are again non-negative. Now, we have the variable x3 less than or equal to minus 3, and certainly we cannot use the variable x3 because our standard form demands that all the variables have to be non-negative. So, let us define a new variable. How do we get that variable? So, we can rewrite this constraint x3 less than or equal to minus 3 as minus 3 minus x3 greater than or equal to 0, and therefore, if we define a new variable called x3 dash such that x3 dash is equal to minus 3 minus x3, then naturally x3 dash will be greater than or equal to 0. So, define x3 dash to be minus 3 minus x3, so that x3 dash will be greater than or equal to 0. So, note that the slack and the surplus variables that we have added are non-negative. Then we have added x1 plus and x1 minus for the variable x1 and x2 plus and x2 minus for the variable x2, such that all these 4 variables are non-negative, and then we transformed x3 to x3 dash, which is defined as minus 3 minus x3, so that x3 dash is greater than or equal to 0. So, these two constraints are written in the form of equality constraints. This constraint anyway is a equality constraints, so we do not have to worry about it. And then the two variables x1, x2 we converted to or we used some extra variables which are non-negative in nature, and the variable x3 was transformed to x3 dash, which is also non-negative. So, we have equality constraints and all the variables are non-negative, and therefore, the program which was given to us can be written in standard form as so, wherever x1 is there, we replace x1 by x1 plus minus x1 minus, x2 is replaced by x2 plus minus x3 minus, and minus 3 minus x3 will be written as x3 dash. So, one can verify that the given linear program now can be written in terms of the newly defined variables, and more importantly, all the constraints which are given here are equality constraints, and all the variables which the linear program uses are non-negative. So, and thus using this or some other ideas, any linear program can be converted to the linear program in standard form. Of course, by introducing some more variables, the number of variables has increased in this case, but nevertheless, we got the linear program in standard form where the constraints are of the type x equal to b and x greater than or equal to 0. So, for most of our discussion on linear program, we will concentrate on the linear program in standard form, and that is why it is very important to convert any linear program to the linear programming in standard form. So, that the theory that we discuss about the solution of linear programs in standard form holds or can be used efficiently. So, now let us consider the linear programming standard form. We will call it as SLP, the standard linear program, where we want to minimize C transpose x subject to x equal to b and x non-negative, and A is a m by n matrix, and rank of A is equal to rank of A appended with B, and that is m. So, A is a full row rank matrix and the rank of A is m. So, this also indicates that B lies in the column space of A and the system of equations x equal to b is consistent. Now, we have m equations in n unknowns and the rank of the matrix A is m. So, we can always choose m linearly independent columns of A to form a matrix B, and since rank of A is m, we can always choose those m linearly independent columns of A. So, in other words, the matrix A is divided into two parts, and without loss of generality, we assume that the first m columns of the matrix A are linearly independent columns, and therefore, the matrix B is formed using those columns, and the remaining n minus m columns will correspond to a new matrix called n. So, in other words, the system of equations x equal to b can be written as where A is split into two matrices, two sub matrices B and n. B is of the size m by m and n is of the size m by n minus m. And remember that the columns of B are linearly independent, and as I mentioned earlier that without loss of generality, we can assume that the first m columns of A are linearly independent. Now, corresponding to those linearly independent columns are the variables which we are going to denote by x b, and corresponding to the remaining n minus m columns, there are n minus m variables, which we are going to denote by xn. So, the system Ax equal to b can be written as like this. And now, if we expand this, so it becomes bxb plus nxn equal to b. And suppose we let xn to be 0, then what we get is bxb is equal to b. Now, note that B contains linearly independent columns and there are m such columns. B is a m by m matrix. So, B is invertible. So, bxb is equal to b means that xb is equal to b inverse b. Now, such xb is called the basic variable or the set of basic variables. So, xb denotes the basic variable associated with the basis matrix B, and since we have let xn to be 0, so xb and 0 gives us what is called the basic solution associated with the basis matrix B. So, the variables corresponding to the linearly independent m columns are called the basic variables, and the solution xb equal to b inverse b along with xn equal to 0 is called the basic solution associated with the basis matrix B. Now, this basic solution helps us in characterizing the vertex of a feasible set, provided that solution is feasible. So, we will see more about basic feasible solutions and its and the characterization of vertices in the next class. Thank you.